Gnanam paramam dheyam. Knowledge is supreme.
We have started our discussion on how wave functions can form bases for the irreducible representations of different symmetry point groups. So, today to start with, we will focus on electronic wave functions, atomic and molecular orbitals, but then we will leave that discussion, and after this we will go on to vibrations. We will come back to electronic wave functions maybe next week, towards end of next week or week after. So, before we proceed any further, tell me what an orbital is. What is an orbital? Yes, right, it is an acceptable one electron wave function. So, if you are talking about an atom, then we talk about atomic orbitals, and when we talk about molecular orbitals, they are also acceptable one electron wave functions for not the atom, but the molecule. So, in principle you should be able to get molecular orbitals by solving Schrodinger equation in elliptical polar coordinate for something like H2 plus, but then nobody does it because it is pointless. You would not be able to solve the Schrodinger equation for anything else. So, what you do is you have different ways of preparing the molecular orbitals. So, let us talk a little bit about atomic orbitals first, but even before that, why do we even care? Why do you care about symmetry of orbitals, atomic or molecular? We care because symmetry and degeneracy go hand in hand. This is something that you have learned when you discussed particle in say 2D box. Remember particle in 2D box, right? If you have a square box, then the 1 2 and 2 1 states are degenerate. Does that ring a bell? Do we remember? Nx equal to 1, Ny equal to 2 and Nx equal to 2 to Ny equal to 1. These two states have the same energy because it is Nx square by Lx square plus Ny square by Ly square. In this case Lx is equal to Ly. So, this Lx square plus Lx square Ly square both can be equated to L square and you can take it outside the bracket. Do we remember this? What about a rectangular box? Now 1 2 and 2 1, these are non-degenerate. Here they were degenerate. Degenerate, as you know, means same energy. So, we build upon that concept, and now that we know about character tables and now that we know about irreducible representations, we can do a little more detailed discussion of this phenomenon that symmetry and degeneracy go hand in hand. So, the reason why we do this is that it helps us simplify the actual quantum mechanical problem if you think of symmetry. A lot of terms become 0 and all, so we can handle it a little easier. So, we will start with something that is very, very familiar to us. Let us talk about say d orbitals to start with. Okay. We know very well that in free metal ion, d orbitals all have the same energy, right? They are degenerate. However, if you put the same metal ion in an octahedral field, then what happens? They separate into Eg and T2G sets. Okay. Now, if I want to do this discussion from the point of view of symmetry, what I need to do first of all is I need to remind ourselves of the form of the wave function of the d orbitals. This is the wave function for 3D x square minus y square. So, why do we call it 3D x square minus y square? Because if you look at the wave function, what do you have? You have a constant, then you have r square, that is the capital R dependent part of the wave function, multiplied by e to the power minus zr by 3a, that also is part of capital R dependent part of the wave function. The angular part is sin square theta cos 2 phi. Okay. This is your dx square minus y square orbital. Now, what is cos 2 phi? How can I write cos 2 phi? Cos square phi minus sin square phi. What do you have in the wave function? You have cos 2 phi multiplied by sin square theta. Okay. So, this whole thing is multiplied by sin square theta, sin theta cos phi whole square minus sin theta sin phi whole square. Now, what is sin theta cos phi? What is sin theta cos phi? Remember r theta phi, right? So, r cos theta equal to z, r sin theta cos phi is x, r sin theta sin phi is y. Okay? So, sin theta cos phi is x square divided by r square, isn't it? And what is sin theta sin phi whole square? Y square by r square. So, it boils down to x square minus y square by r square. Let us not bother about the notes for the moment. Let us not bother about the picture for the moment. Let us just look at the function. So, you can write the function as something in r multiplied by x square minus y square. That is why you call the orbital dx square minus y square. So, if I want to know how this orbital transforms in response to different symmetry operations, what do I have to do? I have to see how x square minus y square transforms. Are we clear? Okay. Similarly, if you go to xy is r dependent part multiplied by constant multiplied by sin square theta sin 2 phi. What is sin 2 phi? 2 sin theta cos phi. So, what do you have? 1 sin theta multiplied by cos phi multiplied by 1 sin theta multiplied by sin phi, that is xy by r square. That is why this is called dxy orbital. So, this orbital is going to transform in the same way as the function xy transforms. Z square is the one I like most, right. In Z square what you have is 3 cos square theta minus 1, and you can say right away that it is 3 z square by r square minus 1. Okay. That is why you call it 3d z square. But let me also tell you that z square is actually a nickname. What is the full label for dz square? Yes, because instead of r square you can write x square plus y square plus z square. So, from there you can get full label is going to be 2z square minus x square minus y square. Okay. Now, this in different point groups you use either z square or 2z square minus x square minus y square. Now, let us look at the character table for the octahedral group. Okay. Remember what we have learnt here, that symmetry and degeneracy go hand in hand. So, if we have functions that belong to a 2-dimensional or 3-dimensional representation, then they are going to be degenerate. Okay. Now, if you look at the character table, see xz, yz, xy belong to T2G, okay, and 2z square minus x square minus y square and x square minus y square jointly form the basis for EG. Okay. What does that mean? That these 2 d orbitals are going to have the same energy, these 3 d orbitals are going to have the same energy. So, just by using symmetry without anything else, I can tell that d orbitals should get split into 2 different groups. One is T2G, one is EG. Okay. And this is why you call them T2G and EG, because it comes from the Mulliken nomenclature of the symmetry species. Now, what I cannot tell just by using symmetry is which one we will have higher energy, which one will have lower energy. For that you have to use electrostatics or common sense or quantum mechanics, depending on the degree of rigor that you want. So, from common sense understanding of electrostatics, I think in class 11 or 12 we learned which one will be lower, which one will be higher. Yeah, Eg will be higher in energy than T2G. Why? Because these are if you take this dx square minus y square and dz square, then they are along the axis. So, electrostatic repulsion will be more, that way you can figure out which will be higher, which will be lower. Okay. So, Eg is higher and T2G is lower. Now, let us think of Jahn-Teller distortion. Jahn-Teller distortion means you have a nice octahedral complex and by some means you pull out two of the axial ligands, or you can do a compression also, pull them out. So, the moment you pull them out, it is not AB6 anymore. So, it is something like this is a central metal ion A. I hope my diagram is not difficult to understand. What I am saying is the 4 A ligands are in a plane that is perpendicular to the plane of the board, and these I just call them B. Which point group is it now? What is the principal axis of symmetry? C4. Do we have a perpendicular C2 axis? So, take this AMA line, you turn it by 180 degrees, that is C2. This is another one, and you think of the bisector of the AMA angle, that is also a C2 axis. So, you have this 4 C2 axis. Okay. So, what will it be? It will be D4, and next thing to ask is, do I have a horizontal plane? I do have a horizontal plane. So, it is D4H. Okay. In octahedral case, we had this Eg and T2G. Okay. The moment you have Jahn-Teller distortion, the symmetry point group changes from an octahedron to D4H. Now, let us see whether Eg and T2G remain intact upon going to D4H. This here is D4H and see what we have. I think I will go there, that is better. Now, see, XZ and YZ belong to the same symmetry species, XY is different, right. Earlier we had a triply degenerate symmetry species, that is where XZ, YZ, ZX belonged, not anymore. Now, XY belongs to a different symmetry species than XZ, YZ. And what about your x square minus y square and z square? X square minus y square is here and z square is in a different point group. So, what this implies is that you cannot have these what used to be the Eg orbitals, you cannot have them degenerate when you have Jahn-Teller distortion. From symmetry itself I can tell that. Okay. So, which one will be higher, which one will be lower? If I pull the ligand out, yes, one is z, so this is z direction, this plane is xy. So, I am pulling the ligands along z out. So, increased electrostatic interaction for z or decreased? Decreased, right. So, will that be stabilized or destabilized? Stabilized, right. So, it will be something like this. Which one is this? Z square or x square minus y square? And this is x square minus y square. What I can do is, now that I know, I can say that the lower one is A1G and the higher one is B1G orbital. Similarly, there will be a splitting here. So, here XZ and YZ is in one symmetry species xy is in another symmetry species. By similar arguments, which one will be lower in energy, which one will be higher in energy, right. If I want to write the Mulliken nomenclature, what will I write? Eg is the lower one and the higher one is B2g. So, you see, just by using symmetry, we can get at least a qualitative idea of what to expect in the energetics of orbitals in different kinds of symmetries. Okay. Now, what about your tetrahedral complex? For that, I have to look at the character table for TD. See here, once again, what you have is 2z square minus x square minus y square and x square minus y square belong to E. Now, you do not call it E to G because there is no center of symmetry, and there is no need to use 2 also because there is only one 2-dimensional symmetry species, you just call it E, and x, y, y, z, z x jointly form the basis of T2 point group. Okay. So, once again you will have 2 groups of d orbitals in a tetrahedral complex, but which one will be lower, which one will be higher? Will the order be the same for octahedral? It will be exactly the opposite, because now the ligands are disposed between the axes, there is no along the axis approach. Okay. So, for that, so what I am trying to say is that symmetry tells you what to expect, it tells you groups of how many orbitals you will get, but it does not give you the last word. You still have to think of electrostatics to understand which orbitals will have lower energy, which orbitals will have higher energy. Okay. So, this is how symmetry can make quantum mechanical problems simpler, right. To close this discussion, we are in this course we are trying to study spectroscopy. So, now what we have understood is that these d orbitals can have different energies in different fields, right, and we can rationalize it in terms of symmetry. What about the transition moment integrals? Let us see. Let us talk about the octahedral field, octahedral case. You have T2g, you have Eg. What is the transition moment integral going to be? Psi 2 mu psi 1, right. As usual, instead of mu, we will work with the x, y and z components, okay. And do you find it difficult to understand if I write like this? What I have done is that I have essentially written 3 integrals together. In any case, the orbitals are the wave functions are the same. So, I have just written x, y, z. So, what I mean is that there is a short form of writing integral psi 2 star x psi 1, integral psi 2 star y psi 1, integral psi 2 star z psi 1. 3 integrals just written together. Are we clear with this notation? Now, see, in octahedral case, it is very simple to tell you that d orbitals are actually symmetry forbidden. Because in octahedron, you have a point of inversion, right. So, this is a Girardet orbital, isn't it? Eg T2g, both are G, symmetric with respect to inversion. This is also G. It does not matter from which orbital to which orbital transition you are talking about. What about x? What about y? What about z? Where do they belong in octahedral field? X, y, z jointly form the basis for T1u, right. And in fact, if you are only talking about inversion, you do not have to talk about x, y, z together, just think of x. Isn't it antisymmetric with respect to inversion? Same is true for y, same is true for z. So, this is u. So, what is the product of g, u and g? It is u, right. That means the integrand is antisymmetric with respect to inversion, and therefore, it does not survive. The integral does not survive. The integrand is antisymmetric with respect to inversion, that is why the integral does not survive. That is why, as you know, dd transitions are actually symmetry forbidden, alright. Of course, what happens when I go to an octahedral field? Now, it is not so easy, right. I do not have a center of inversion. there I have to consider everything, all symmetry operations, and see whether the triple product contains a totally symmetric representation. Okay. For now, we will not go into that, we will come back to this in a later class. Okay. But before we leave this topic, let us quickly remind ourselves where we stopped yesterday about molecular orbitals. Molecular orbitals. So, what we have shown you yesterday is that even molecular orbitals actually form bases for irreducible. Before we go there, is there any question in what we discussed so far? Yes. Oh, we erased it. This you do not have a problem, right, if I just write A everywhere. Now, if I write A, well, in Jahn-Teller distortion, what I am saying is that these two axial ligands have been pulled out. That means they are distinct from the equatorial ligands, right? Sorry? The bond is longer, right? So, what you can also do is you can talk about the bonds, you can name the bonds like that. I will exaggerate a little bit, this is the figure. So, I call these bonds AA, I call this bond B, I call this bond B. Now, it is not very difficult to see that B and B are equivalent, but different from the 4 A's. We just talk about the bonds, think of bonds as vectors, the lengths are different. Sorry, we look at the shape of the molecule, not just ligands. So, bond length is also important, right. So, of course, I mean what you expect is that if you have say ABA, then AB bond length should be the same, right. But then if you do a distortion here, why does Jahn-Teller distortion take place anyway? Yes. So, the bond lengths are not the same, isn't it? So, since bond lengths are not the same, think that we are looking at the bonds, we have a way of looking at the bond lengths, this is what the picture is. So, if you work with the bond lengths, do you understand that it is going to be D4H? That is good enough. It is not only ligands, it is the shape of the molecule, do not forget. If the ligands are for some reason placed at a larger or smaller distance, then the symmetry changes. So, it is equivalent to replacing the axial ligands by two different ligands. Yes. Sometimes we get slight DD transition. See, we will come back to that, wait until we do a little more detailed discussion of electronic spectroscopy. So, what happens is forbidden transitions are not always there are ways of working around forbidden transitions. So, you can have things like spin orbit coupling, by which the wave function is not what you would expect it to be without any correction. So, the wave function itself is a little changed. Perhaps we can understand it if we think of what happened for anharmonic oscillator. See, for harmonic oscillator, what was the selection rule? Delta V equal to plus minus 1, right. What about anharmonic oscillator? The selection rule was delta V equal to plus minus 1, plus minus 2, plus minus 3, but probability of transition kept going down steadily from plus minus 1 to plus minus 2 to plus minus 3. Why? Because in anharmonic oscillator, it is a part of system, right. You do not have pure wave functions anymore. Due to mixing of wave functions, the transitions like delta V equal to plus minus 2 that were forbidden earlier now become allowed to some extent, right. Similarly, you can have mixing of orbitals by different means, spin orbit coupling being one of the most major reasons, we will come to that, or you can also have something called vibronic coupling. So, when we talk about benzene, for example, you will see that a transition that is supposed to be forbidden is actually the most prominent transition in benzene that we see, and that is because of what is called vibronic coupling, coupling of electronic and vibrational motion. Okay. Let us wait for that, we will come there. Okay. So, where we stopped yesterday was these molecular orbitals, right. So, let us just quickly see where the molecular orbitals would belong. We have already worked out in the previous class. Let us take a simplistic scheme here. What we are saying is this 1s and 1s give you linear combinations to give you say sigma 1s and sigma 1s star. Then 2s and 2s atomic orbitals give you, oh, there is no space on the top, that is a problem. One s and 1s give you sigma 1s and sigma 1s star. 2s and 2s give you sigma 2s, now I will write here, sigma 2s and sigma 2s star. What about 2p? We consider the direction of approach of the two atoms to be the z direction. So, 2pz and 2pz give you sigma interaction. And these give you pi interaction, px and py. Okay. This we already established, right, that whenever you have bonding orbitals between two s orbitals, what is the symmetry species? What is the irreducible representation? It is totally symmetric, right. What do you call a totally symmetric representation in d infinity h? Sigma g plus. So, I can say that this is, and there are different ways of writing this. I can say this is sigma g plus, this is also sigma g plus, this, what about this? When 2p orbitals give you a sigma bond, what is the symmetry? What does the molecular orbital look like? Something like this, right? Right? So, let us see quickly what the characters would be. For E, character is 1. For C infinity, what is the character? 1. What is the next symmetry operation? Sigma V. Where is sigma V? This plane of the board. Of course, there are many, but I can take the plane of the board. What is the character? 1. What is the next one? S infinity. S infinity means you turn by this and reflect with respect to this. What is the character? 1. And finally C2. This is C2. What is the character? 1, right. So, even this is sigma g plus. So, what I can do is I can write this as 1 sigma g plus, 2 sigma g plus, 3 sigma g plus. Different books use different notations. You can use whatever is convenient for us. What about the antibonding orbitals? Remember what was the antibonding orbital? We worked it out yesterday. Antibonding orbital sigma, something like this. For E the character is plus 1. For C infinity the character is plus 1. What is the next one? Yes, sigma, sigma V, yes, sigma V. What is the character? 1. Then what is it? I, oh I missed I in the previous one, but no harm. For I, what is the character? Minus 1. Then S infinity, what is the character? S infinity is also minus 1. And finally C2, C2 minus 1. So 1 1 1 minus 1 minus 1 minus 1, 1 1 1 minus 1 minus 1 minus 1, it is sigma u plus. So all these antibonding sigma orbitals can be written as, say 1 sigma u plus, 2 sigma u plus, 3 sigma u plus. I am only left with the pi orbitals now. Pi orbitals do not belong to a one dimensional representation. Let me draw them like this. This is Z that is defined, okay. Is it difficult to understand if I draw the p orbitals as arrows? These two arrows denote the p orbitals of the two atoms, and these two arrows denote the px orbitals of the two atoms. The vertical arrows denote the py orbitals of the two atoms. Are we clear? How will they transform? They will transform exactly like x and y axis. We do not even have to work it out, it is given here. Where do x and y belong? Pi u, alright, pi u. So, the bonding orbital here is actually pi u. You can work this out yourself and convince yourself that these two px and py, two sets of px and py actually form basis for pi u when it is bonding. What about the anti-bonding one? When I write xy, I mean px, py. This is a situation for anti-bonding. Where will they belong? Once again, they cannot be a basis for a one dimensional representation, because the issue is this is x, this is y, right, like this. Where is C infinity? C infinity is towards u. So, if I do a rotation with respect to C infinity, what happens? These transformed coordinates cannot be written in terms of only px or only py. The transformed coordinates have to be written as a linear sum of px and py, there is no other way. That is why they jointly form the basis for a 2D representation. Now, this is a situation that we have done already. What I am asking you to do is this 2D representation, work out where it will belong. One thing you can tell me right away, is it G or is it U? It is G, isn't it? Look at my thumbs and look at my index fingers. Do you see the center of inversion? Right? Right? So, it is G, actually it is pi G. The antibonding pi orbital is pi G. So, this is how you write it, how you write the names of the molecular orbitals in terms of symmetry. The next thing to do is symmetry of states, okay. But before I go there, I think it is better if we complete our discussion of vibrations of polyatomic molecules, then we will come back to this, okay. So, we close this discussion here, we will begin vibrations after this.